And his title is The Role of Michel Hénon in Detecting Regular and Chaotic Dynamics in Conservative Systems.
I have to give the microphone.
Non, mais c'est parce qu'il faut changer.
There is some technical issues before. Tu peux m'enlever mon micro? Je vais mettre à l'air. Il faut le mettre à...
Tiens, je te mets ça dans la poche. Tu as pu le mettre?
Oui, mais écoute, je crois qu'il est gouverné de l'extérieur.
Tu mets ça dans la poche? In the bag? Bon, dans la poche, ça ne marche pas. Attendez, pourquoi je vois rien?
Ça me fait penser.
Ah, maintenant. Ok. On voit quelque chose dans l'écran? Non.
Oui. Oui, non, je te dis, c'est effectivement un peu isolé dans son œuvre. Oui, d'accord. Saturne. Ah oui, oui.
Voilà. Bon.
Oui, même
l'infinité des...
Ah oui, oui. Oui, oui. Ah non, mais d'accord. Non, mais c'est clair que difficile d'anticiper. Totalement.
Let me show you this picture but for the moment being I shall hide this picture, okay? Because I would like to show you something else. And let me start by saying that I was very lucky. I knew Michel Hénon in the middle of the 70s, I think in some conference in Besançon, probably. And then I had the opportunity to talk with him several times at his office at the Observatoire de Nice, his marvelous office, from which you could see the Simò on one side, the Alps on the other side, excellent place. And I must say the following, he was a very nice person, discussing with him, it was excellent all the time. And he told me once that he was considering himself as an experimental mathematician. And I think this is right. He did many experiments, but he was extremely clever because the main idea was to extract the relevant information from many systems, okay? And I am indebted to him because, in fact, I use several of his examples, discrete maps, conservative, dissipative, Hamiltonians, etc., in master and PhD courses. Right now I have students which are fighting with theoretical or numerical aspects of the Hénon-Hales potential or variance. Okay. Then, let me, this working?
It works. Yeah, but
if I don't put that thing, it will not work. Maybe. Yeah. Then let me start with the quadratic array preserving map. This is a very simple example. This is exactly the same map as shown by Jean-Christophe, but in the case of, this is the pointer. Is some pointer here?
Yeah. No.
Oh, yeah. But it has different versions. One version is take this map, one of the so-called Jonquière map, and make a rotation by angle alpha. Or this is exactly the same model as shown by Jean-Christophe in the conservative case. some term in Y here is missing clearly. But I prefer a different version, is the version which appears here, which is obtained by a modification, change of scale, etc., introduce a new parameter. In that case, I don't know why I cannot see the full screen, probably have to shift a little bit. Or I should do something different, change the scale. Okay. Then in that case, they should use, for the conservative case, the parameter b equal -1 to have it conservative and area preserving. This version has an advantage. The advantage is that it's quite easy to go to the limit when c goes to 0, and then you have a limit Hamiltonian flow. And another advantage is that the fixed points are always located at -1, 0, and at 0, 1. This is an illustration using this formulation, the classical formulation of this map. I mentioned that here y is missing. And what is the geometrical meaning? Geometrical meaning is very simple to understand. Take a square like this square in red, then you make a deformation in a quadratic way. You have something similar, but with a parabolic shape. Then you rotate by an angle of 90 degrees, and you have this image. And then you iterate the map. And then when you iterate, taking this square, the next images are the one in blue, the one in magenta, etc. And when you keep iterating, you have a set of points which never escapes. This is the set of points which remains in the Hénon map. Okay? Then here you have an example of orbits in the Hénon map for a small value of the parameter c, 0.2, and a larger value, 0.752. Here you see that the dynamics seems very close to the dynamics of a vector field, but here you see a central domain, some islands of period 5, and you start to see some teeny chaotic domains here close to the hyperbolic points of period 5. And what is important is that finally you have around that, you have some invariant curve. Okay? These curves will be destroyed when you change the parameter, and then the chaotic domain located here is able to escape. And this is what produces the changes in the measure of the set of points which subsist. Okay? And here you have the vector field announced, which is Hamiltonian, corresponds to this shape. I would like to direct your attention, this is made for the non-quadratic map, that the line in blue, okay, is the unstable manifold of that point, and this line in blue is the stable manifold. And it seems that they coincide. They don't coincide. And I would like to introduce here something which is important to understand many other topics. And the thing which is important to understand other topics is what happens with the splitting of these separatrices. Okay? Then it is possible to show in this formulation that there is a homoclinic point located on the x-axis. Then we can measure the angle between these manifolds at that point. And if you do that, and you plot in a true scale, this is a parameter c, and this is the value of the angle, and you see that it decreases to 0 quickly. Of course, you should be aware that most of the work of Hénon, especially the paper with Hylas, was done in 64, but I think computations were done in 62. In 62, almost nobody knew about KM theory. Almost nobody knew about the fact that the complement of the tori is exponentially small. Nobody knew about the fact that there are many phenomena which are beyond all orders. But all these things are inside the work of Michel Hénon, as I shall try to convince you. Then, beyond making some presentation of mentioned results of Hénon, I would like to pose some problems, some exercises, no? And this is the splitting measured at that symmetric point. Then you can see that for values of the parameter less than 0.2, it seems to be 0. But if you plot that in logarithmic scale, you see this plot. This is in logarithmic scale for the parameter c, and this is logarithmic scale for the value of the splitting. All this means that you have to compute with several thousands of digits, but this is a technical detail. It's an elementary exercise. But this is known. But what is not so well known, and maybe some people in the audience has done contributions to that. I don't see Zozen here. No, okay. And is the following. Look at the splitting. Then there are theoretical results derived several years ago by Ernest and myself that that prove that the splitting angle should be of the form some constants, maybe some powers of the parameter. In that case, no power of the parameter shows up, an exponentially small term, and then it can happen that there is a correction factor. In the present case, this is a constant, okay, exponential of minus 2 pi squared. There are good reasons to show that this has to be this coefficient minus 2 pi squared. I shall comment on that later. And h of c is the logarithm of the dominant eigenvalue at the hyperbolic fixed point. And then there is a correction factor. If you look at this correction factor and you compute with sufficiently large number of digits, it's possible to expand that as power series in this parameter h. And then an experimental fact is that if you plot these coefficients multiplied by 2 pi squared power 2m divided by 2m plus 6 factorial, and you compute that for several hundreds of coefficients, you have the plot here. Okay? The coefficients increase, and then it seems that they clearly tend to some constant. This would prove that this series, okay, is not some arbitrary formal series, but is a series such that it has a algebraic character. This means that if you take the Borel transform of this series, this formal series expansion, you have that the Borel transform is an analytic function and has radius of convergence 2 pi squared. This is an open problem. Okay? But what is more important, and this was of course not known at the known time, is the relation with the so-called Chirikov standard map. Let me go to the Chirikov standard map that can be written in different ways. For instance, that way that I put here. xy goes to y bar, which is y plus a constant k sinus 2 pi x, and here x plus y bar. Then, it can be defined in the two-dimensional torus, therefore you can take x and y modulus 1, or in the cylinder. You take x modulus 1, but you keep y in the reals. It is known that invariant rotational curves exist that prevent diffusion until so-called Green's critical value, which is 0.97 divided by 2 pi, because I have a scale here using this version, which is roughly that value. For the standard map, this Chirikov map, or standard Chirikov-Taylor, there are several names, you can also have some hyperbolic fixed point. You can compute the splitting of the separatrices of this fixed point, and you have the curve in blue. Okay? Sorry, you have some splitting. I shall comment in a moment. But you can also measure, as a function of the parameter, okay, measure in red, which is the fraction of chaotic points on a torus. How to measure that? Oh, this is an easy exercise. Just take a grid of points, compute the Lyapunov exponents, use some good criterion to decide when a Lyapunov exponent is 0 is positive, and look at how many points have positive Lyapunov exponent, which is the measure of that set. And you have, as a function of the parameter, you have the plot in red. Look, this plot is not in real variables. It's plotted in an exponential way, as we saw in the previous image. Okay? And this is a fit by a function which would be of this type. This is the fit on the blue. We have a fit. You see that, well, the behavior looks quite nice, close to some theoretical prediction. But what is more important now is the following. Take the standard map for large values of the parameter. This value, this computation here, and you look for the moment in the torus, has been done for a value which is a little bit larger than 1. You take a point, and to make sure that this point is not in any island, take the point in the unstable manifold of the hyperbolic fixed point. Cannot be in any island. And then you do iterates. You plot 100,000 iterates, and you have the red points here. But then you look at the complement. And if you take points in the complement and you magnify, you have this structure. And this structure looks very similar to the structure of the node map, when you have a central point, some islands, some invariant curves around, islands of period 4, and some curves around it. Okay? Well, this is not something unexpected. In fact, Chirikov already guessed something about that, but we obtained recently a proof, which is the following. There is a limit behavior of the dynamics around two fixed points, and around the period 2 and period 4 orbits of the MK is the standard map. And under suitable scalings in the variables and in the parameter, for the parameter near an integer or the parameter near an integer plus 1/2, the limit maps are conjugated to area preserving or area preserving orientation or reversing orientation Hénon maps. In the same way that we showed here before the area preserving, orientation preserving Hénon map, there is a similar map which is area preserving but orientation reversing. Okay? And I have it in some other slide, but it's irrelevant. Then this means that in the standard map you see close to integers you have here something, and this something is in some sense a copy of Hénon. Okay? Well, but what is more surprising is the following, is that if you go to the previous slide and you can measure also, take a grid here, well, typically I take something like 100 million points and some tricks, compute Lyapunov exponents and measure how many points have positive Lyapunov exponent, and which is the measure of the set of points with regular dynamics. Okay? And the measure of the set of points with regular dynamics, okay, has this behavior. You see that close to, I started close to 2. Close to 2, there is some kind of domain, narrow domain, in which you have regular dynamics. The measure is small, of the order of a few thousands. Close to 2.5, something similar. Close to 3, etc., etc. This repeats, and this is an image of the previous result. But the interesting thing, and also an image of the previous result, is that if you take this and you scale in a suitable way, you get this plot. You get this plot. And different plots in different colors corresponds to the images of that, etc. Okay? And what you have here is, under some scaling, a kind of two concatenated copies of the Hénon map. You have here a copy of the Hénon map, and you have here a copy of the Hénon map. What I mean a copy of the Hénon map? If you look at the measure of the set of points which don't escape under the Hénon map, it's exactly that shape. Okay? Well, this is a result, but is it relevant concerning dynamics? Let me go to the following. In that domain, if you take a point here, okay, you can imagine that if you look at the dynamics of an initial point in that chaotic domain, the dynamics for large values of k will be standard diffusion. Therefore, you expect that there is some coefficient which depends on the value of the parameter k, and then the standard deviation of the iterates behaves as proportional to the square root of the number of iterates. Standard diffusion process. Okay? Well, this is true for many values of the parameter, but not for all. And then this plot, this picture here tries to exemplify a little bit this fact. If I compute some kind of normalized, etc., standard deviation parameter from the iterates, and I divide by the square root of the number of iterates, using a fixed value of the number of iterates, say 1 million, what I get for the standard deviation of a set of random initial points is that this behavior. You see that it follows, it is close to constant. It is not exactly constant. There are some corrections which depend on Bessel functions, and these are due to the correlation of successive iterates, and were derived already in the 80s by, for instance, Lieberman and Lichtenberg. But then there are some peaks, which correspond to the so-called existence of accelerated modes. And this gives anomalous diffusion. How can we understand this anomalous diffusion? This is computation of standard deviation, which is, we should expect something close to constant if this is really a diffusion process, and you have this plot. But then if you look at the small domain here, and you magnify and you look at the detail, different colors correspond to different number of iterates, and you see different peaks. And if you try to realize these peaks to what correspond, and here this is a magnification using increasing and increasing number of iterates. And you see these bumps, and you see these satellite bumps, etc. And if you try to identify which is the reason of that, you realize that the reason of all these things is a non-map. Let me tell you what happens. That value here, for instance, which is the more prominent one, appears for a value of the parameter which is related to a value of the parameter in the non-map, which is just a little bit after the destruction of the last invariant curves which surround the period 4 islands. This one here corresponds to a little bit after the destruction of the last invariant curves which surround the period 5 islands. This one, period 6, period 7, etc., and these are supermonics, period 9, rotation number 9 over 2, etc., etc. Why? Well, it's easy to understand. Because if you have some domain, it has invariant curves. Points from outside cannot enter. Okay. But when the invariant curves are destroyed, they are replaced by Cantor sets. Then it is difficult, there are some gaps in the Cantor set, they can enter inside. The probability is small, but if they enter, they can be inside that Cantor set, the domain bounded in quotation marks by this Cantor set, for a long time. And therefore, if you are located in a place such that under the initial standard map, what it's doing at every step is, let me go to the standard map. The following, look here, what happens if you have a value of x which is close to 1 over 4. The sinus that you have here takes the value 1. This means that in one iterate, the value in y jumps for k units. Okay? These are the so-called accelerated modes. And this can be, you can be inside that island. The value of x can be close to 1 over 4 for many iterates. And you jump every time for a constant value. And this destroys completely the expected diffusion on the system. Okay? There are some nice statistical properties. I'll say let's keep that. There is still a series of problems, and we are studying with some students now. We are working on that, trying to obtain a good statistical description of the problem. Okay, let's keep that. And let me go to the non-Hilus Hamiltonian. I would like to look at the non-Hilus Hamiltonian for a while and closely related systems and some generalization. This is a Hamiltonian, and then we can look at Poincaré sections on y equals 0 for energy, say 0.1. And this is what you get. Let me try to magnify a little bit the image. In that image, you have, for instance, this, like that would be enough, yeah. You see that there are 1, 2, 3 points which are hyperbolic, 1, 2, 3, 4 points which are elliptic, and of course the periodic orbit around. Total 5. Should be 5, of course, no? Because if you have 3 hyperbolic points, and we should have 5 elliptic points because the characteristic of the sphere is 2. Okay? The sum of the number of hyperbolic points minus the elliptic points minus hyperbolic should be 2 according to Poincaré-Hopf. Okay. What I would like to stress also is that you have some amount of chaos here. Okay, you see. And you have these points, and you can compute the invariant manifold. I have plotted the invariant manifold in one color and for that point here, and in another different color, the stable manifold of that guy. Then it's very hard to see the splitting, but for that purpose, if I magnify, and this is quite easy, you can see easily the oscillations of one manifold with respect to the other. You see here, this is the stable manifold of that point, and this is the stable manifold, okay, which follows blah, 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 and will be close to, by lambda lemma, do the unstable manifold of that point, which goes like that, but I have not plotted to prevent from too many lines. Okay, then you have two different objects. One object is the amount of chaos, the other object is the splitting of the manifolds. Do they have some relation? Okay. Well, then let me go to Michel's paper. And what is amazing is that he obtained that result. And what you have here is the fraction of regular orbits. This means this is the energy, and this is the fraction of regular orbits. And you see that up to some energy like 0.10 or something like that, it seems that the system is regular. Come on, this cannot be true. If there is some analytic property, should hold up to 0. Okay, it cannot be true that this up to some place it is integrable, and from some place on is not integrable for analytic systems. But what is marvelous is that he was able, together with Carl Hess, to do this computation 51 years ago with the computers at that time. Now the most powerful computer at that time is nothing compared to a single mobile telephone. Okay, but this was exceptional achievement. Okay, and gave an indication about the lack of existence of the third interval of motion, etc. If I repeat this computation, but I do that for exactly the same values, and with some more detail, using many points, etc., the correct plot is that one. And then you see that, well, for 0.1, there is some fraction of chaoticity. The fraction of chaoticity, therefore the regular motion, is almost everything up for energies which are around 0.070 something. We can do exactly the same thing as before. Therefore, I can plot here in some scale, and the suitable scale is plot the logarithm of 1 minus the regular fraction times h. Why I do that? Because if I know that if this has something to do with some splitting, in the splitting I have a term which is exponential of minus constant divided by energy. If I take the logarithm, I have constant divided by energy. If I multiply by energy, I should be a constant, but there are other terms in front of it. Constants, powers of the energy, etc. Okay? Then this is the result of the amount of chaos that we have, and this is a fit by a formula of the standard type I mentioned. And then I can do the following. I can compute the splitting angle at the points that I have seen before. This means the symmetric points. Compute the splitting angle here, okay, at the symmetric point. And then you have this plot. This is a splitting angle. This is, again, the logarithm of the splitting angle multiplied by the energy, okay, and fit by a theoretical formula according to what we expect to have. And this is the fit that I had previously, except some constant factor and due to the results of separatrix map, okay? And this is the fit, this is the value, in red, the value that one has obtained from the measure of the chaotic domain. Therefore, we see the chaotic domain is mainly due in that problem up to energy, say, 0.12, to the splitting of the manifolds. What happens after? Why after will be not exactly so good fitting? Why you see here, if you look in detail, some kind of oscillations. And this kind of oscillations is easy to understand. Because in the Hilus problem, you have also islands. These islands are associated to some period, okay? They have associated hyperbolic periodic points. These hyperbolic periodic points have some chaotic domain. When the invariant curves around this domain are destroyed, okay, they increase, this chaotic domain increases the total measure of the chaotic domain. Okay. But I said at the end, there is a nice relation between the measure of the chaotic set and the splitting of the manifolds of the periodic hyperbolic orbits. This can be expected now, but not in 1962. Okay? Question. What would happen if Hénon simplifies the model and skips the term in 1/3 of x cubed and takes this other Hamiltonian? Is one of the Hamiltonians known to belong to the Hénon family. Okay, I do exactly the same. I compute on the section on y equals 0 for that value of the energy. And then you have this section. You have one hyperbolic orbit here, 1, 2, 3, 4 elliptic points. And of course, the boundary orbit has to be hyperbolic again. Okay? So that 4 minus 2 equals 2. Okay. Then you see some chaotic domain here. Oh, well. And you can compute exactly the same as was computed by Michel in 62. This is the fraction of regular motion. And you have a surprise here. And the surprise is the fraction of regular motion. Oh, by the way, so if you want to have a bounded domain, the Hill region has to be bounded, you have to take energy less than 1 over 12, 1 over 8. Therefore, I stop. The computations are 1 over. And the fraction of regular motion has this shape. It increases, there are some irregularities, and it seems that it reaches the value 0. But after that, you decrease the energy, and the fraction of regular motion decreases. Okay? Here I have the complement, the fraction of chaotic motion. It decreases, it's chaotic motion, but at some moment it seems to be 0, but then you decrease the energy, and the fraction of chaotic motion increases again, and it decreases here. And if you are careful, and you do some magnification, but then one has to use too many points, you see that this structure that it increases, decreases, increases, decreases, is repeated infinitely many times. Okay. Then here what we have, okay, is the splitting of the separatrices, okay, computed as a function of the energy. Separatrices where? This is a more delicate problem. Here you have a manifold. Maybe I can magnify. The stable and unstable manifold is that hyperbolic point. If I magnify for that value of the energy, they seem to be almost coincident, one in blue, the other one in magenta, but if you magnify somewhere like here, you see that there is finally a difference between the two manifolds. Then it's possible, I shall not enter into details, if somebody interested I can explain later, it is possible to normalize that, etc., and to plot the difference between one manifold and the other, okay? But instead of looking at the angle at a given point, in that case there is no symmetry at all, there is no homoclinic point in some symmetric line, what I do is something different. I look at the total measure between one homoclinic point and its image. I mean, take a homoclinic point like this one. The image of that point is that one here. Therefore, you have here some oscillation of one manifold over respect to the other, and here the oscillation. Look at the area enclosed in that domain, and look at the area enclosed in the domain and add them. Take the absolute value of the areas. Okay. Then, what happens is the following. What happens is that if you plot in a suitable logarithmic scale, etc., the amount of chaos, it has this behavior. Okay? If you plot in a suitable logarithmic scale the amount of the splitting, measured as an area, you have this behavior. If you plot the experimental one, the amount of chaos and the theoretical fit of the splitting times a constant, you have this behavior. What happens? And what happens is that the splitting is not just some angle which is decreasing to 0 exponentially, but the angle oscillates. And why this can happen? And the reason is quite simple. To study the splitting of separatrices of simple maps like this one, what you have to do is look at some limit flow. It's possible to derive the existence of some limit flow in the Poincaré map, and this flow is Hamiltonian. This flow has separatrices. And then take one of these separatrices and look at the singularities of these separatrix in the complex plane. If the singularities lie on the imaginary axis, then you have something exponential decrease, some exponential decrease. But if they are outside, they have a real component, you have something which I try to put here, I think in the next slide, okay? which is that thing, no? You have something which is exponentially small times a correcting factor which contains a cosinus. Then the amplitude of this thing will be 0, but one moment, amplitude of what? The behavior of one manifold with respect to the other can be put in as a periodic function. And then when you have a periodic function, what you do? What you do is, okay, let me do Fourier analysis. This is the amplitude of the dominant harmonic, the first one. But then, when this amplitude is 0, what plays a role is the second harmonic, okay? Which is an exponentially small with a double exponent. And this is what seems that it decreases to 0. It's not true, okay? Well, just to finish in the last minus 1 minute that I have, let me comment that it would be nice to see what would happen if Michel Hénon, instead of looking at the one-to-one resonance with 2 degrees of freedom, would look at the 1-1-1 resonance with 3 degrees of freedom and with a Hamiltonian term here, a cubic term, which is completely non-symmetric. I dislike symmetry. Symmetries are okay to understand something, but then you want to perturb. Then look at that system, and if you take values of A, B, and C, which are different, for instance, A less or equal B less or equal C, you can normalize to sum equal 3 or sum equal 1, whatever. The question is, how does the fraction of chaotic motion behave when the energy tends to 0? Should we expect also that the fraction of chaotic motion goes to 0 when the energy goes to 0? And the answer is, of course, not. And here you have some illustrations. This is the fraction of regular motion for some selected values of the parameters. 0, 3/2, 3/2, 0, 1, 2, 1/2, 1, 3/2. This is the fraction of regular motion when the energy decreases. And the fraction of regular motion tends to a constant, typically much less than 1. Okay. Why? All these systems are non-integrable. And in next slides, I shall skip, I give how this is proved using differential Galois theory, okay, theoretical approach. But then, the important thing is that you have a system in 1-to-1-to-1 resonance, but 3 degrees of freedom. In the normal form, you have, when you compute the normal form and you truncate, is a first integral. The second order terms, another first integral. But you miss an integral. The limit system is non-integrable. Okay? And this is what explains why you have this behavior. Therefore, if you try to extend Michel ideas to these kind of things, okay, then let me conclude by saying the following, last slide. There is an infinite amount of things to understand, but guided by Michel Hénon insight and in these prime K-paradigmatic models, understanding these models gives the basic ideas to understand many other phenomena. Thanks, Michel.
Thank you. Maybe one question or comment? No? Okay, so thank you again. And we reconvene at 11.